Thanks a lot, Sylvain. I appreciate the introduction. I also wanted to thank the organizers for the opportunity. Too bad that I cannot be in person, but maybe next time. I also wanted to tell you that technically, for some reason, I can't see the chat. So if there are questions, actually feel free to interrupt. You can, I certainly don't mind that, maybe the organizers do, or you wait till the end and ask them. But unfortunately, since I am sharing my screen, I actually don't see the chat. There's that. So the, excuse me, the first lecture is about objective barriers to passive transport. The second one will be about diffusive and active transport. And you will see, hopefully see the difference. I find this image very motivational. This is a image from a professional photographer, Dania Beltra, that I have found very inspiring, showing structures in the ocean during the Gulf oil spill. And I think you might see this picture coming up again, but the main motivation is or the main message from this picture is that there are very well-defined structures in the ocean that govern the transport of all sorts of things, not just in the ocean, but in other flows. And over the past, I would say probably 20 years, there's been substantial progress in understanding these. And I'd like to talk about that, some of it, if you just excuse me for a second, because I need to move things around here. I want to remove the laser pointer and just put this in the middle. Okay, and come back to the pointer again. Okay. So this is an outline of the lectures, a very quick one. So I want to give you first the motivation for these barriers that I'm going to discuss in the first part of the lectures. And these go by now generally by the name of Lagrangian coherent structures. And I want to talk about the relevance, observability, and very importantly, their objectivity. That's also in the title. And after that, one can go two different routes. Either one starts discussing a mathematical theory for these, which there exists, and there are lots of papers and review articles and formulas, or one goes in another more practical direction and says, based on the physical properties of these, can we come up with diagnostics that, without necessarily being, statements of theorems, but still being relevant, can give us some quick idea in given velocity fields about these structures. And this is the route that I'm choosing for this lecture. For the next part of the lecture, that will be more mathematical about the other subjects. So you will see both approaches. So for these, for passive mixing, I will give you more of a diagnostics-based approach, and for active and diffusive mixing, more of a bit more mathematical approach. But both exist for both, right? So different flavors. So there will be some objective diagnostics that I want to talk about, and I'll clarify the word objective in a second. For sure, I'll be talking about three, and if I have some time in the end, I'll be talking about some more recent ones that are applicable to single trajectories, and they don't require multiple trajectories. And in the end, I also want to talk about objective Eulerian coherent structures, which are a somewhat recent development. They are instantaneous limits of Lagrangian coherent structures. So basically, the idea is, if you believe that Lagrangian coherent structures are the right thing to study, but you would also like to understand them in a more instantaneous sense rather than over a period of time, then you can certainly take that limit and you enjoy the benefits of observability, objectivity, but you will no longer be tied to a particular time scale. I also wanted to list some references. I wrote an annual reviews on this in 2015, which I guess is contains a lot of this material, but since then there's been further developments. And if all true, then finally this year, this book that I've been working on with Cambridge University Press will be appearing sometime, perhaps in the second half of the year, and will be available. And that covers basically pretty much all the background material. Or part of that book will be Jupyter notebooks that a student of mine has been developing. Alex Encinas Bartos has done a great group work on that, and the primary purpose of this is to support the book, but the notebooks are largely done, they're out, and you can actually download them from this address, or you can just simply go to my webpage. I'll give you the address and get to them. And they implement pretty much almost all of the methods that I'm going to be talking about in the book, or the ones that you can see in the review. So what's the motivation for these Lagrangian coherent structures or LCSs? And again, please forgive me for a second. I constantly cover up the part of my screen that actually has titles in it. So I still want to see those somehow. That's shifting things around, if at all possible. Okay, so what are these? Instead of giving you a definition, I give you pictures first and then maybe a physical definition. It's usually natural disasters, unfortunately, that make us stare at the atmosphere or the ocean, or at least inconvenient events. And you see tornadoes picking up dust on the left here. And certainly that's an unwanted phenomenon. Although there are people who make a living out of taking close photos of them. You see a person here, there, and clearly this is a devastating weather event, and you want to get out of the way, but people don't always manage to get out of the way. So sometimes they get injured. So that's certainly something that is very spectacular and not necessarily positive. The oil spill that I have mentioned, the Gulf oil spill, was another event that brought various patterns in nature, in flows, into the focus of attention. And also there was this earlier, I forget the year, but another, perhaps not a natural disaster, but this volcano eruption somewhere in Iceland, if I'm not mistaken, that ejected a lot of dust and volcanic ash in the air, and all of a sudden it was a major impediment to air traffic in Europe, and you could see these structures in the air. So this always gives new impetus to trying to understand what structures in complex flows we have, and how we could better understand, model, and perhaps extract them from models or measured velocity fields. But you don't have to necessarily think such large scale. They also appear at the micro scale, say microfluidics. You see various patterns in flows. Back to the large scale, and more exciting kind of recent application is the possibility of geoengineering, where people have been speculating whether just by injecting large amounts of aerosol into the atmosphere, you could mitigate the impact, the greenhouse effect, and basically slow down global warming. And that brings up the question, how best could you deploy these large numbers of particles from airplanes so that they get mixed the best, and they don't get captured and hence just circulate over given regions. So that's certainly an area in which there's been related activity. And search and rescue, that's actually an example I'm going to get into. What you see here is patterns of floats, ocean floats or drifters over a period of 2 years, 96 and 97 in the Gulf of Mexico. And what's amazing about these is that these seem completely random, but if you see that this mysterious barrier that I'm showing here, that pretty much none of them crosses. You might say I'm exaggerating because some of them cross it, and also you might then wonder why they cross it on such straight lines, right? And you might even wonder further why they then continue. This is now land, right, in Florida. So how come that those drifters keep going? And the answer is that curious fishermen occasionally pick up the drifters that oceanographers use for research purposes. The minute it's on a ship, you see that it's gonna go, of course, go through any transport barrier that it would normally have, and it's a straight line, and finally it ends up in somebody's pickup trucks, and then the person is driving them home, hence the straight line. But without all those additional ways of propulsion for the buoys, they would actually respect this barrier. So the question arises that if you then try to rescue people who are floating essentially in the Florida waters or elsewhere, are there perhaps barriers that would help you narrow the search so that you would prefer certain regions and exclude other regions, thereby optimizing your resources? So that's another area. So after all these sort of hand-waving examples of Lagrangian coherent structures, what are they physically? I would say these are centerpieces of observed tracer patterns. So in all these cases, you see tracer patterns, and if all goes well, then somehow they have a theoretical centerpiece, right? They have finite thickness, but the physical view is that perhaps in the middle of any of these objects of finite thickness, there is a material surface in 3D or material line in 2D that's acting as the organizing center. And the question would be, can we actually identify that from velocity data without having to simulate the evolution of various substances or invest a lot on that just from velocity models or even sparse velocity data? Can we locate where they are? It's not clear where they are. Importantly, we see the impact of structures in the flow. Those structures are there in the flow even if you don't throw particles there. If there would be a twister here, and if there was nothing for the twister to pick up, you would just see through that twister. Right? What you see there, the reason why you see that structure is because there are tracers there, and the tracers then, to varying degree are highlighting this or getting attracted or being repelled. So what you see there is more like a footprint of the structure rather than the structure itself. Similarly, in the ocean, you use tracers to highlight, to get some information about these structures, but the footprint is not equal to the structure itself, right? The footprint has finite thickness to begin with because that's how the oil got dispersed, right? That doesn't change the fact that there would be material structures at work, even if there was no oil spill there in the ocean. And it's a fair question to ask, what are they? Can we even see them or visualize them even when we don't have the vehicle or the freedom of throwing traces in there? And can we perhaps even predict their evolution? Mathematically, LCS would be then some sort of distinguished material surfaces that act as a centerpiece for a reason. So why are they a centerpiece for these patterns? Because I would argue because they're locally the most, or even perhaps the least stretching or shearing material surfaces. So they have some distinguished mechanical property that makes them to be the centerpiece of that object. And the minute you start taking this point of view, that actually leads you down on a more mathematical direction, because you can say, okay, so let me actually formulate variational principles for these objects: most attracting, most shearing, least attracting, least shearing material surfaces. These do lead to variational problems. They are hard, no question, but then we can actually go after exact solutions of those fully supported by mathematical theory. Whereas the first part, and that's what I'm going to capture or cover in the first lecture, the first type of approach is more physics driven, and it's aimed at more giving you quick diagnostic tools that you can run on velocity fields to find these structures. Before I go into that, I think one of the important, to me, the realization that this fact that I'm going to talk about is important, which is a major game changer in terms of the types of methods that I was developing. Namely, at the end of the day, I'd like to detect structures, or most of us, I submit to you, would like to detect structures in the flow that you can later then verify experimentally. So as a main objective, I would set for any theory that's supposed to be about these structures or transport barriers, that it has to be experimentally verifiable. And that has a long, what sort of tools do we have for experimental verification? This is Ludwig Prandtl's historical flow visualization, where he first did this. I mean, with this movie, he basically established the whole area of flow visualization, where you basically see structures near an airfoil, and in a camera that's moving with the airfoil. So then these vortices are being shed and they disappear out of view. But this is I think he used aluminum foil. So these are material particles that visualize that. Now the camera is staying still, it's not moving. So it's the same vortex built by the exact same material structures, but the shape of the trajectories that delineate these structures are different because you're looking at it from a different frame. Clearly, Prandtl already realized that even though the two frames are different, the trajectories of individual tracers are different, but the material objects that they delineate better be the same. Otherwise, we will never come to a conclusion. Different observers will pronounce different regions or different particles as being part of a vortex, and others that are not being part of a vortex. So already there, the birth of flow visualization, somehow independence of observers in terms of visualization was important. When you look at any current images of flow visualization with more advanced tools, they still involve materials, either smoke or dye, but material objects. These are the ultimate arbiters, whether something is really there, they inspire you, they tell you what you would like to model or explain and what you would like to verify. If the method that you're applying doesn't have this ability, that it does not produce materially observable structures, that it may be very good for other purposes, but not for the purposes of understanding barriers to material mixing or material transport, because those are fundamentally material behaviors. Okay, if your interest is for some reason, as many people's interest is, for instance, drag or pressure, those are not material notions. If your interest is the magnitude of the velocity at some point, these are not material notions. But if your interest is mixing and transport of material stuff, then whatever theory you come up with should be conforming to that and should be returning the results that do not just depend on your position as an observer, but general position. He should be independent of the observer. I find this very inspirational. NASA took 30 years of buoy data and initialize them at the same time and let them run. And when you do that in the ocean, again, amazing barriers to transport become visible. The picture is thinning out because, not all buoys have the same lifetime in the water. So they have to be taking, there's fewer and fewer buoys that have long trajectories, right? So most buoys don't have a maximal trajectory. That's why it's thinning out. That's why they're sort of disappearing. But ultimately, they reveal what? Material structures in the ocean. So if you keep that in mind, then the lesson that I'd like you to kind of accept or think about is that flow visualization reveals a material behavior, okay? And material behavior is objective in the sense of continuum mechanics, namely, it's indifferent to the observer. And continuum mechanics is a very good way of quantifying that historically. It says, let's think of all the observer changes that are realistic physically. So what can an observer do relative to another observer, a human observer? For the purposes of observations, you can't squeeze them, you can't stretch them. What you can do, you can rotate them in an arbitrary fashion relative to each other. Hence, when you change from the X coordinates to the Y coordinates, you have to allow for a general time-dependent rotation tensor, both in 2 or 3D, and you can shift them arbitrarily. So if you are claiming to have, or you would like to have conclusions about material mixing, and you accept the fact that material mixing should be experimentally verifiable and material, and hence independent of the observer, then your conclusions should be independent of whether you're in the X coordinate system or the Y coordinate system, and with respect to all choices of this rotation and all choices of translation. Mind you, this is not some sort of esoteric expectation for symmetry. There wouldn't be a nice kind of thing. No, it is a must, because the minute you have conclusions that are not indifferent to these changes, then you might be detecting something, but it's not about the material response of the flow, because that is indifferent to the observer. That's an axiom in continuum mechanics, right? So coherent structure theories consistent with flow experiments must necessarily be objective. And I was very proud of myself when somehow I was trying to articulate this, 15 years ago, maybe more, until it was pointed out to me that, lots of people well before me had the same idea, as always, right? So I don't claim to be somebody I claim to be somebody disseminating this. I'm a big fan of this, but very insightful people, even in the 70s, in the fluids literature, especially in the non-Newtonian flow literature, laid down this principle that whatever you use for diagnosing coherent structures, important structures in the flow, the quantities you're using should be objective. And these are some of those references. So mine is really just sort of a rediscovery of that. I can't really claim that I was the first one. Well before me, people have realized this, okay? Yet, and here's the big however, is that all classic criteria that are being currently used in any fluid dynamics meeting or most fluid dynamics articles for finding, there's a typo here, this should be structures, for finding barriers or structures or coherent structures, they are not objective. They don't conform to these requirements. So these fantastic pictures that various codes will produce to you, or the pictures that you see at most meetings, however intriguing they are, and however intuitive they are by now, because people are using the same tools to visualize the same flows, okay? However believable they are not objective. And it's easy to see why they are not. Most of them use the velocity gradient, one form or another, and in particular, this partition of the velocity gradient into a spin tensor, which is the skew symmetric part of that, and a rate of strain tensor, which is the symmetric part of it. And if you look at how these transform under frame changes, so when you change from an X to a general Y frame with that rotation and translation, then the spin tensor, which in the new frame you would recalculate after transforming the velocity gradient, doesn't transform as an objective quantity would have to transform. An objective quantity, a tensor, would have to transform, if it was objective, according to the rules of continuum mechanics, as a general linear operator when you change from one frame to another. And this would be that part of the transformation. This is how you, if you ever learned in linear algebra how to change bases for a linear mapping or linear operator, after you've rotated the basis by a rotation matrix Q, then this is the formula that you learn from. If it's not a rotation, but a general coordinate change, you would have Q inverse here, right? Then it wouldn't be a rotation matrix. And that's how we are used to changing linear operators like the spin tensor from one frame to the other. Unfortunately, that's not how it transforms. It has an additional term minus Q transpose Q dot, okay, that comes in. And that makes it non-objective. That's not the problem for the strain tensor. The strain tensor transforms properly, as they say in continuum mechanics. So if people just use the strain tensor and inferred things from the invariance of the strain tensor, that wouldn't be an issue. But they use a combination of the two. So, excuse me, any criterion you may have heard, the Q criterion, delta, lambda 2, and all these are non-objective because they are using a combination of these. I'll get to that maybe at the later part the lecture. Now, is that really a problem? I mean, a lot of people would say it's not a problem. I don't care about objectivity. I just want the truth, right? If that is even possible to get without being objective. But more seriously, if your criterion returns one result in one frame, and then you simply don't change the frame for the flow. It's not that you're putting your flow in a rotating tank. That would change the flow. No, you're only changing the observer. You're putting the observer in a rotating tank that has nothing to do with the physics of the flow. And that observer then computes different results, okay? Then again, if you're interested in something that's material, intrinsically related to the fluid, then you should not be satisfied with that. And unfortunately, all of these criteria have that property. And just to give you an illustration, this is an exact of where that leads you. Well, basically, you can start doubting any of your results. This is an exact linear solution of the 2D Navier-Stokes equation that I kind of threw out just, I think, something like a long time ago, 2005. I didn't even assume that it's the solution of the Navier-Stokes equation because I thought surely it's probably not, right? But it's just a kinematic example. And then about 15 years later, it occurred to me to check. And it does solve the Navier-Stokes equation. This paper that we wrote is about a whole class of explicit solutions that you can derive unsteady solutions and for the 2D Navier-Stokes, and this is one of those. So it's just an unsteady velocity field. It's linear, spatially, and the unsteadiness is time periodic. Okay, and if you run any of these criteria for that are meant to decide whether you're in a vortex or outside a vortex, all of them will agree and say that it's actually a vortex globally. And if you look at the streamlines, let me step back, and they are time dependent, but at each and every point in time, they're closed, okay? So that really just tells you, well, this should be a vortex, right? So by all these criteria, for all you know, it's a vortex, okay? If you then try to verify that by putting tracers as if you were doing an experiment, just initialize tracers in one of these, it's now in a different position. And this is my collaborator, Javier Beronvera from University of Miami, did this movie a long time ago, but I still keep using it from him. And then let them go. And let's see what a flow visualization experiment would give you in this case. Then this is what you get. Sorry, I jumped too quick. I have to step back because this movie for some reason doesn't want to. Yeah, okay. See? Particles go to infinity. So in fact, what this is a saddle point. But in each and every frame, if you believe in streamlines or believe these criteria, it will be pronounced as a vortex. So this is how bad it can be, right? So everybody says this is a vortex, but those depend on the frame. And in reality, it's a saddle point. And in fact, if you evaluated the same criteria in an appropriately moving frame, somebody magically gave you that speed, then they would tell you that it's a saddle or it's hyperbolic. So that's the issue with the dependence on the frame. Now, I want to, this is the one last thing I want to say about this. I can't resist it because I think to me, in fact, this is more important than individual diagnostics. It's more of a principle that I think is very important from continuum mechanics because it really guides your intuition and kind of, for me, it provides a litmus test for everything I do or my group does. Does it conform to the principle of objectivity? Because if it's not, then it might be something that's useful for some other reasons, but for material mixing and transport, I should forget about it. That's sort of the litmus test for what I do. And as I communicate this litmus test, people tell me, no, you're wrong. You know, that might be true in mechanics, but fluid mechanics is not mechanics, according to some. And the argument that I usually hear back is the following. Okay, on the one hand, solid mechanics says, and this is an actual quote from a very influential book of one of the biggest names in continuum mechanics, and I quote it literally, verbatim. One of the main axioms of mechanics is that material response should be independent of the observer. And that's the process of a long and tedious process. People fought this out sometime during while Einstein was active, first in physics and then in mechanics. Right now, if you submit a constitutive principle for consideration by your peer groups, and it's not objective, people will not talk to you because they have adopted that as a litmus test, okay? And people say, okay, that's fine in mechanics. And what do you actually mean by that? Well, specifically, I mean that what they mean is the conclusions about material response should be indifferent to all frame changes on this form, okay? And then comes the counter argument that this is completely irrelevant in fluid mechanics. So I'm paraphrasing an argument that I heard many times, is that objectivity is irrelevant in fluid mechanics because even the Navier-Stokes equations, which are the fundamental equations of fluid mechanics, they are not objective. And when people say, because think about it, if you change to a rotating frame, and I'm not even doing translation, it's just changing the frame from X to Y with time-dependent rotation, you can define the vorticity of the frame change as the vector such that if you take its cross product with any unit vector, then it's the same as applying that. Remember that Q transpose Q dot extra term? If you apply that tensor to A, that's always it's like a rotation. So there will be a well-defined, you could say angular velocity of the frame change or something. In this case, that because the frame change is actually quite simple, say steady rotation speed, much the same as what you do when you try to understand geophysical fluid dynamics in the frame of the Earth, right? So this is not even a general frame change. It has a general angular velocity constant. So that's actually constant. So this is just a simple setting, okay? How does the Navier-Stokes equation change based on that? And you learn this in geophysical fluid dynamics that black was the original Navier-Stokes, then you have an additional Coriolis term and the centrifugal term, right? There you go, goes the argument. Even under the simplest but relevant frame change, the Navier-Stokes equation has changed. So what do you want with objectivity? I mean, you're just basically trying to sell us something that's irrelevant in fluid mechanics. So they said there's a contradiction between the two, right? So before I go any further, in fact, read the solid mechanics quote a bit more carefully. It says one of the main axioms of mechanics. It doesn't say solid mechanics. It says mechanics, and fluid mechanics is part of mechanics. So if it was wrong in fluid mechanics for the equations of motion to change in different frames, I mean, sorry, that it would somehow invalidate the principle of objectivity, it would invalidate it for the whole area of mechanics, because guess what? This is just Newton's equation of motion. If you write Newton's equation of motion for solids too, and you pass to a moving frame, it will change and it will have exactly the same terms added to it. So what? The people in solid mechanics somehow didn't realize this, somehow they overlooked this. So there seems to be a contradiction. Well, there isn't one. This is a misreading of the principle of objectivity. Nobody said that the equations of motion should be invariant. The principle says that the material response should be indifferent to the observer, the material response. Nobody requires the velocity to be invariant on the frame changes, not in fluids, not in solid mechanics. But we want conclusions about material behavior to be indifferent to the observer, okay? So what does that mean? Say, in this case, we actually go by that. That's our axiom in fluid mechanics as well, which is material response from the Navier-Stokes equations is objective. If something is a trajectory, material trajectory in one frame, then it should be the image of that under the transformation should be a material trajectory in the other frame as well. So if something, you have a velocity field in one frame, and this is a trajectory of that velocity field, then if you transform the Navier-Stokes equations in a new frame, you get a new PDE with all these additional terms, then it's guaranteed that the trajectories of that velocity field will be transforming to the old trajectories, even though you can't even solve for them explicitly, but they will be transforming to the untransformed trajectories by exactly the same transformation that you applied to change the coordinates. Now, how do I know that? Because I clearly don't have a magic formula to solve the Navier-Stokes equation. I know that because this is how we derived the Navier-Stokes in that frame to begin with. We engineered it. So this was the frame change, right? And then what we do, we differentiate this. This is how we start, because that's how we relate velocities to each other. Now, why don't I get zero when I differentiate space with respect to time? I mean, space is independent of time, right? So when I differentiate x with respect to t, I should be getting zero, same for y. No, I'm not getting zero, because I'm not just differentiating space, I'm plugging in the trajectories to begin with, and I link them via this transformation. So this is what I'm doing. I'm immediately, right at the very first step, constraining the trajectories to be mapped into each other, okay? So everything else starts from there. Then I differentiate this, I get velocities, and this is how we derive the Navier-Stokes equations in the new frame. So generally speaking, excuse me, if you switch to a new frame, which is completely general, not just a uniformly rotating one, okay, some crazy frame, maybe a quadcopter frame, which is really doing crazy motion. The only recipe we know for deriving the equations of motion is applying the principle of material objectivity, which is we start from this relationship, which is now more general. It's, you know, it has translations and cues. We differentiate it in time, and that step guarantees that the material response from both the old frame and the new frame, even though I have no explicit solutions for Navier-Stokes, will be related precisely the way they should be. So that's the answer to the apparent contradiction. Objectivity is just as well upheld in fluid mechanics as it is in solid mechanics. In fact, this is the lifeline of fluid mechanics when we want to derive equations in new frames, right? So this is just one thing I wanted to emphasize, and that's why I'm only talking about objective diagnostics here. So there will be, if you read the literature, there will be any number of heuristic or some actually even mathematically derived arguments, but I'm only focusing on objective ones which comply with this requirement. Otherwise, if it's not objective, I have no reason to believe that it captures material behavior. In fact, it cannot, because if it was objective, then it would be indifferent to the observer. So again, numerical implementations of these are available either in these toolboxes, or you can go, if you don't remember this GitHub link, you can just go to my website. So what are some of the objective diagnostics that help you?
Sorry, George.
Go ahead.
There is a question on the chat. The question by Mukesh is the material objectivity same as material invariance?
That's a good question. For reasons, the ideas of material objectivity or frame indifference were introduced by Truesdell and Knoll, the two giants of continuum mechanics. And I think they also kept changing the term. They may have used material invariance, or some people use material invariance. It's meant to convey the same, but there's been a shift to this other term, indifference rather than invariance. Invariance suggests, broadly speaking, that the equations or the quantities that you're looking at do not change at all. And that's not the case. You've seen how you have a tensor in one frame, you describe the rate of train tensor, you write it down in another frame, it will always change, the entries will change. The question is, how will it change? Will it change consistent with the definition of how linear operators should properly transform? So does it transform as a linear operator should be? So generally speaking, that's the term I use, that material frame indifference or indifference to the observer, which means it's not that the quantity remains the same, but it transforms properly, following exactly the observer change, okay? Because one even material trajectories in one frame, remember Prandtler's experiment, the vortex was leaving this way in one frame, and the other frame, it was standing still. So you can't say that the two trajectories are invariant with respect to the frame change. They are not, right? But they are pointwise related. And for that reason, if that trajectory or vortex is materially distinguished in one frame, it will be distinguished in the other frame as well, okay? But one frame change can make a looping trajectory completely straight. So it's not, that's why I would not use the term invariance. An exception is scalar fields. Scalar fields transform properly when they actually do not change. So if you talk about a scalar diagnostic, which I'm going to talk about a lot, then invariance and indifference, material invariance and material indifference are identical expressions, because the scalar field is objective if it doesn't change under changes of coordinates. But that is not the same for vector fields and tensor fields. They both have vector field and tensor fields have different transformation rules under which they are objective. There's another question, I think, that.
Yes, the second question is by this again. Okay, does the Euler-Lagrange duality not address this point?
I'm not sure what that is, to be honest. Maybe we can come back. I don't know what the Euler-Lagrange duality is. We can come back to that maybe after the lecture, and then I would learn what that means.
Okay, yes.
I mean, in the discussion session. So how do I move on? Okay, so the first such diagnostic, in fact, historically, this is the first one that was developed in this area, is the finite time Lyapunov exponent, FTLE. That goes back a long time. And I have to say that also that many people identify the whole area of Lagrangian coherent structures, which probably has been around now for what, 20 years, with FTLE. You see lectures on YouTube and everything, Lagrangian coherent structures are whatever, FTLE. That's just one particular diagnostic. There are many others and in many different flavors and deliverables. Let me talk about FTLE first. This is an objective diagnostic scalar, which means that it does not change after transformations of the frame for hyperbolic LCSs. And again, this is not a mathematical lecture. This part one is a physical lecture, so I just rely on your intuition. A hyperbolic LCS is a material surface that distinguishes itself because it's locally most attracting or locally most repelling, okay? So either attracting or repelling, and FTLE is good for the detection of these, locally most repelling or attracting. But it also turns out that it's also good for the detection of parabolic LCSs. And the way you could devise a variational principle to describe parabolic LCSs are their least shearing. So I show you pictures here. These are from my annual reviews article, and there are proper credits to the pictures there, which I forgot to put here. What you see here, is, excuse me, is this wave. I forgot what wave we call these. This is a special name for these waves, but what it is basically it's the when you have two recirculation cells meeting at the coast, and then you will have this upwelling from the coast away, and people love riding in those because they basically eject you. But in the middle of that, for that to happen, there has to be an attracting material line that attracts from both directions and ejects you, right? And this can be actually very dangerous, and people are taught how to avoid them. You're not supposed to, you want to get out of it because it can take you very far from the coastline. But if you swim in the direction that you would like to swim, you're even helping that. So you're trying to swim away from the push, then it just keeps pushing you. What you need to do is swim out of it. to a transverse direction, which is perhaps less intuitive. But that's an example of a hyperbolic LCS right there in the middle, theoretically, okay, which attracts all these material people. And that would be a hyperbolic LCS. A parabolic LCS would be something like the material core of a jet, such as the Gulf Stream. And this, you here see a temperature picture of that. So, excuse me, the middle of an actual material jet would have the property that an appropriately defined Lagrangian shear is minimal there, because somehow the velocity profiles, you know, profile levels out. So there isn't a whole lot of shear there. It's just, but this has to be defined in appropriate material sense, and you can find that in the appropriate papers. So how do you get to FTLE? Diagnostic field, just take a general trajectory, which starts from x0, and it travels forward. And I'm going to be using the flow map a lot. The flow map, intuitively, if you haven't heard that expression, is just the solution operator of the differential equation for trajectories. The differential equation for trajectories is x dot equals v, right? Where v is the velocity field. And the solution map maps initial conditions such as x0 based at time naught, at t naught, to their later position along trajectories at time t. So this picture defines the flow map, but imagine it to be defined for all initial conditions, and the initial time and final time are fixed in this particular picture, but generally speaking, you can vary them, okay? And you can initialize a little material perturbation to the trajectory at x0, and you might ask, if that's infinitesimally small, how does that perturbation get advected along the trajectory? How does any potential stability or instability develop? And the vehicle for that, as it turns out, is the gradient of the flow map. In differential equations, we call the solution that solves the equation of variation and dynamical systems course. But you can argue that the way that evolves, you just have to take the deformation gradient and apply it to C. And if it was infinitesimally short to begin with, okay, then in that infinitesimal range, this is the accurate representation of that perturbation. If it wasn't infinitesimally short, then you would have order C squared contributions to it. But those are always smaller than the leading order term. So you can ask, what is the length of the deformed lined element? Now, this is objective. I don't do the proof here, but you can imagine that length is something that's independent. Material length and material deformation, change in length, is an objective quantity. You can verify that separately. You can plug in the transformations and check that it returns the same quantity, but I rely on your intuition so that I don't have to do it. So what do? You plug in this end length and square norm of that, but you can write it out as an inner product, right? So you just take the inner product of this advected material line with itself. And then using the properties of a transpose, I grab this grad f here and put it here. So that will appear here as a transpose. And this is what's called in continuum mechanics, this is the deformation gradient transpose times the deformation gradient, the Cauchy-Green strain tensor, okay? And this is therefore, when you look at this quadratic form, clearly the Cauchy-Green strain tensor C calls the shots. And the definition of that strain tensor, again, is deformation gradient transpose times the deformation gradient, okay? And there's a standard estimate in linear algebra, excuse me, that you would learn that if you want to upper estimate this quadratic form, it's very believable, I think, is that you can just take xi norm squared and you take the largest eigenvalue of this tensor. This is a positive definite tensor because of the way it's constructed, essentially squaring, if you will, the deformation gradient. So this lambda max is for non-degenerate flow, it's guaranteed to be a positive number. Okay, and then you can ask the following, because still we would like some sort of this curve to satisfy some sort of extremum property so that it's important. So the simplest diagnostic approach to finding this line here, the theoretical centerpiece of that material spike, excuse me, or in other, sorry, in backward time, that's going to be an attracting LCS. So first I'm going to talk about the repelling LCSs and then come back to attracting ones. So a repelling LCS would be the set of points with the locally largest possible stretching. So I would look for a set along which this eigenvalue is as large as possible. Okay. It's a heuristic principle because I would have to solve a variational principle that eigenvalue is not going to be constant along the curve. Maybe I can pick another curve along which maybe I have nominally pointwise lower, but overall higher. So there are considerations here, right, that are at this stage heuristic. I'm just saying, you know what, I'm just looking at curves along which overall this is the largest, or in 3D, I'm looking for surfaces. Now, excuse me, when you like to do that for a scalar field, then imagine that the height, excuse me, of the scalar field is something you see in this picture, like in a mountain. So you're essentially looking for ridges of that mountain, right? The ridges are not constant. So it doesn't mean that I will be locating a point. It doesn't mean that the level of repulsion or attraction is the same all along this curve, but somehow when I look left and right, I'm still larger than they are. That's the idea of a mountain ridge, right? Which is not constant in time, but along this certain direction, it's higher. Or this is the idea of a height ridge than others. There are various ridge definitions, but this is the most intuitive one. So basically what you want to do is look at this eigenvalue. It tends to grow exponentially. So it turns out it's not a bad idea to take its logarithm. But even before that, I'm going to take its square root because look, the quantity I was interested in, length, I squared that at the beginning for convenience so that I don't have to carry the square root. So why don't I take the square root of that to get actual length? And then this length tends to grow exponentially. So why don't I take the logarithm of that? So the output of that operation will be some exponent times the time that has elapsed. And I'm really interested in that exponent. So I also divide by the time that has elapsed. And I might want to do this in backward time as well. So I actually divide by the length of time. That's why I'm taking the norm of that, because T1 might actually be lower than T0. And I'm looking for, in fact, the most attracting material line. I would actually run things in backward time, and whatever is most repelling in forward time will be most repelling in backward time. So I can apply this in two different directions. And there you go. That's called a finite time Lyapunov exponent between T0 and T1. And this is also a very old concept. Its application to geophysical flows. Probably the first person who had that idea was Ray Pierre Humbert in 1993. Various other people have used the Lyapunov exponent, but not necessarily in a way that I'm describing here. You will not see the argument that I've given here, because usually people tend to look at it as some sort of measure of chaos or complexity or stretching, very often do statistics on it. But the fact that ridges of the FTLE field are in fact indicators of finite time repelling, most repelling material surfaces, I believe I pointed that out in 2001. But the highest cited paper I think still the highest cited paper in the area is not my paper, which I put this forward, but a paper by Jerry Marsden's group, who unfortunately passed away in the meantime, Sean Shadden and Francois Laquien and Jerry Marsden, who took this and gave a formal mathematical definition and also proved that the material flux through these curves is zero or very small. Unfortunately, as people have looked at it in more detail, there are issues with the definition itself. It's only satisfied for straight lines and nothing else, no curves. And that formula for the flux has turned out to be incorrect. So basically all the contributions in that paper have not stood up to the test of time, yet it's very influential because I think that they managed to draw attention to the FTLE as a tool a whole lot more efficiently than I ever was able to do that. So I think that everybody started realizing, they had great examples and everything. Well, if you read these papers, beware that essentially definition results, everything has turned out to be incorrect. Various people have found that, but I think it's still a very important paper. Okay. The attracting LCSs would be the same in backward time. So these would be the ones that I'm talking about here. So since they are attracting in forward time, in backward time, they're the most repelling objects. So you could run a backward time FTLE analysis to find them as regions of the backward time FTLE field. Okay. And parabolic LCSs, this was a very insightful paper by Javier Barón and collaborators that I'm going to cite in 2010 when they said, wait, why don't we just look for maxima of the FTLE field? The trenches of it are equally important. And in fact, those will be these material jet cores here, okay? And they are incredibly robust. I would also like to argue that with these unstable objects, these repelling objects are perhaps less important than jets. I mean, when we talk about the ocean, what do we talk about? Well, structures in the ocean. We talk about jets and eddies, right? Sometimes fronts. So the fronts would be basically these guys because you are attracted to them. But I think we far more often talk about jets, which will be these guys, the cores of which will be the trenches. And we also talk about a lot about eddies and vortices, but the FTLE is not geared towards those. That's a separate subject. The FTLE is all about finding either compression or stretching, and vortices are about something else. So for that, we will need another tool or several others. So how do you compute them? This is very quickly. I know that there are questions in the chat. Should we stop now for questions? And unfortunately, I don't see them.
Yes, there is a question. Is there any advantage using FTLE instead of FSLE, especially about objectivity?
That's a good point. We have a paper on that. FSLE turns out to be, I think that was our conclusion, objective as well. FSLE, I wasn't planning to talk about finite size Lyapunov exponents. Basically, it's a similar quantity, but uses the flow map at different points over different time intervals, right? So it basically looks for more like an end deformation. It plots the deformation as the main variable rather than time is not the same for the different runs. When time is not the same, you're not computing a diagnostics over the same amount of time, then you're not analyzing a given flow map, okay? And then that's where dynamical systems kind of stops, because you know what, we're not familiar with that. We know about the flow map, but different flow maps over different times in unsteady flows, we're not so sure. Also, we have a paper on this with Daniel Karas that shows that unfortunately FSLE brings in, by its very construction, artificial effects, and we analyzed that. There's a whole paper on that. So if you ask me, I know exactly what I'm getting from FTLE. There are mathematical results for FTLE. FSLE, I cannot relate rigorously to Lagrangian coherent structures, and it wasn't for the lack of trying. We have a whole paper on this that you can look up. It's on my webpage, also all these papers. But we also found, to our surprise, that there are persistent artifacts in FSLE definition by diagnostics by the very construct, but they are objective for sure. There's no problem with objectivity. Other questions quickly?
There is a second question by Julian Mack. Are vortices related to the elliptic points?
Okay, we'll talk about vortices a little bit later, okay, and then we can talk about that. Elliptic points, presumably if people mean elliptic streamlines or stagnation points that are elliptic, whatever you read off from streamlines is not objective and very often misleading, okay? Just remember that my little example, which show you closed curves with an elliptic stagnation point, in reality it was a saddle, okay? So I would not relate elliptic stagnation points to vortices, but I will get to that, but although I'm falling behind soon. Any questions left?
No other questions.
Okay, thank you. So I just want to talk about the computation of the FTLE, because the reason, I mean, this has been cleared up by now. This is no black magic. There's any number of little routines that you can download or you write your own. It's really not complicated, but there are some ingredients that come up in this calculation that will be important for other quantities. So basically, there's two fundamental ways you can calculate FTLE, either as I introduced it, the eigenvalue, the largest eigenvalue of the right Cauchy-Green strain tensor. This is simpler because I talked a lot. Remember, this is the maximal eigenvalue of the Cauchy-Green strain tensor. If you have that, you have FTLE, because the rest is just playing around with that quantity, right? So this is straightforward. So how do you do? You have some flow domain, you put down a grid of initial conditions. This is not necessarily, you may know your velocity field at these points. Typically, you will need a denser grid because you will have to differentiate trajectories with respect to their initial positions. That's what the deformation gradient does. But your velocity field might only be available on this G. So what you do, you interpolate the velocity field in between to get to those finer details. Clearly, for that reason, if you get structures from this analysis that are below the grid size, then you have to discount those. But if you get structures that are ranging over several grid points, then they are robust with respect to this calculation. So I just wrote auxiliary grid here. We will be using a smaller grid for the purposes of differentiating trajectories with respect to their initial conditions, because the deformation gradient, which is the fundamental object you need, can be, using finite differencing, can be approximated like this. These are in this direction, you will have the three components of a trajectory: x1, x2, x3, or x, y, z if you are in 3 dimensions. If you're in 2 dimensions, then this would be a 2 by 2 matrix. In 3 dimensions, this would be a 3 by 3 matrix. And what you do for each and every component, you apply an x finite differencing in x, which means that you take this trajectory that runs from t0 to t and perturb its initial condition in the positive x direction, say in this direction, okay, and launch a trajectory from there. Then perturb the initial condition in the negative x direction, that's what I'm doing here, and launch another trajectory there. Take the difference of the first coordinates of those two at your finite time and divide by the distance between these two perturbations, which is here. So you're finite differencing the first component of the solution in the first direction. Then you do that for the second component of the solution. You're finite differencing over perturbations in the third direction, then to the third component, okay? When you're done with that, you will do the same to all 3 components or 2 components of the solution, but now you're perturbing them in the x2 direction. So this delta 2 perturbation will be, say, a perturbation upwards. And then I subtract delta 2, the perturbation downwards. I launch trajectories from those points, and I evaluate their difference at the final time t, and I divide by the distance between those 2 points. And I do this for 3 components, and if I have a third dimension, I do that in the third dimension as well. I perturb the initial condition in the z direction, plus z, plus delta 3, plus minus delta 3. Again, take the difference, divide. So this is a very well-defined numerical finite differencing procedure that approximates the deformation gradient at each and every grid point, right? So basically, you have to store for a 2-dimensional flow, you have to store a tensor field over the grid points, a 2 by 2 matrix at each and every point. If you're in 3 dimensions, you have to, at each and every grid point, you have to store a 3 by 3 matrix. So if you have a very high grid, then of course the computational costs will go up. But in my annual reviews, you can find references. People have figured out how to do this more efficiently. You can also parallelize this very well, all sorts of things. So that's less and less of a problem. Okay. So the main objective is not the deformation gradient, but the Cauchy-Green strain tensor. Okay. And you basically have it because once you have these locally stored, then you can locally calculate the Cauchy-Green strain tensor. And the minute you have the Cauchy-Green strain tensor in 2 dimensions, you can by hand calculate its eigenvalues because we have a formula for that. In 3 dimensions, say numerically, or you could use Cardano's formula, and you can calculate it. And then you obtain a scalar field at each and every grid point, okay? And the idea is look for regions of that scalar field. And if you've done this calculation in forward time, there will be a repelling LCS. If you've done it in backward time, it will be another LCS. Another way is to calculate these quantities from a singular value decomposition, because this is exactly how the eigenvalues of C are just the singular values squared of the deformation gradient. Singular value decomposition, I just remind you quickly, is writing a matrix like this as 2 rotation matrices, U and V, with in this case, a diagonal matrix in between. Generally speaking, if it wasn't a square matrix, then this sigma would not be diagonal, but in this case, it's a diagonal matrix. And the diagonal elements of that will be the square roots of these eigenvalues that we would be using here, okay? And one advantage of doing this, you will still need to do the finite differencing, right? Because you have to decompose grad f, and that you need to have before you do this decomposition. But one advantage is that the U and V matrices arising will have a meaning on their own. The U will be the left singular vectors, which actually come up as eigenvalues of another strain tensor, which is not the right, but the left Cauchy-Green strain tensor that has its own significance in some of these theories. And the V are the right singular vectors, which are the eigenvectors of C. And I haven't talked about those yet, but only the magnitude of the eigenvalues, not the eigenvectors, but those turn out to be giving you directional information. So they are kind of the most stretching directions, right, at that point, right? And there are many other diagnostics that need these vectors as well. So I would argue that this is probably the most efficient and quickest way. You can't get around the finite differencing approach, or you might have some other approximations, but you do need to have a numerical approximation for grad F. But then rather than calculating eigenvalues, it actually turns out to be more accurate even to calculate just a singular value decomposition. And it basically gives you everything that you would ever need for any objective Lagrangian diagnostic, not just the eigenvalue, not just the maximal eigenvalue, the minimal, everything in between, left and right eigenvectors. And basically, and it's just almost like one command in MATLAB. Okay, this is an old example from the time that we were first playing with these ideas. This was an experiment by Harry Sweeney's group, two-dimensional turbulence in a tank, so a rotating force by jet, flow force by jets from below. Okay, and the velocity field was available with high accuracy. And when you calculate the FTLE field over the velocity, it's supposed to be two-dimensional turbulence. This is what you get. Look how noisy these are, right? So these are the ridges that you get. This is the FTLE field. How did we compute this? This will have a connection to this workshop in a second, a more direct connection that I'm going to reveal, but now I'm holding that information back for a second. So how did we calculate this? Well, basically you have a velocity field, very well resolved from particle image velocimetry. Use that velocity field, launch trajectories, simulate trajectories, okay, and do the finite differencing that I have told you. And then if you plot the FTLE field, it's very noisy. So to get to the ridges, you want the ridges themselves, you could use gradient climbing methods. So basically build a gradient system out of this. Sigma is just the FTLE. So then that generates trajectories that actually converge to the ridges, but also you have to filter the ridges themselves as well. And since I'm not showing the reference, this is the unexpected, very direct connection with this workshop. So Mani Mathur is one of the organizers with whom I was very pleased to catch up again, was the leading figure on this paper. This was part of his PhD thesis at MIT, and he was the very first one who was able to do this well on a real life data set. And you see when he came back with these pictures of attracting and repelling LCSs, we all were stunned. And to this date, I know from colleagues when they teach nonlinear dynamics, some of them in the US, good schools, they're using this picture to illustrate how complicated turbulence is. And those, if you know a little bit about chaos theory, if such a thing even exists, homoclinic and heteroclinic tangles, horseshoes, then those, not only are those prevalent and present in simple time periodic flows, as had been known, but also in flows with general time dependence in an appropriately generalized form. They are not anymore, stable and unstable manifolds of fixed points, but they are attracting and repelling LCSs. And you see the two colors. And the repelling ones, the red ones constantly push you away. The blue ones attract you, and the combination of those just results in turbulent mixing. You can also identify generalized saddle regions. I'm not going to go into that here. It's in this paper. There's a criterion that you can, and that's a mathematical objective criterion that tells you where the actual generalized saddle regions are. They are no longer points. They are little open sets. So this was another example, and this is, as I mentioned, Javier Beron-Vera and his collaborators at the University of Miami pointed out that the FTLE could also be used, the trenches of the FTLE field, to find jet cores in a material sense, not in a Eulerian sense, instantaneous, minima of Eulerian shear. Those would not align with these structures that you would infer from instantaneous plots of streamlines, but this is in the appropriate material sense, and these we call parabolic LCSs, and you can get them very accurately as trenches of the FTLE field. This is a different flow, the Bickley jet example. PRA, so this has been all about hyperbolic and parabolic LCSs, fronts and jets if you want, but have not been talking about vortices at all. And a student of mine Mohammed Farazman, who's now a professor of mathematics in University of North Carolina, was involved in all this. He was always very keen on us going in this direction, that also look for elliptic structures as well, have some objective diagnostics for elliptic structures, which is elliptic something material vortices, right? Not vortices inferred from streamlines or anything, but infers it for the purpose of material mixing, such as the one you see here, the great red spot of Jupiter. That's a material picture. You're seeing different gases being mixed or unmixed, and this is unpenetrated. This is the size of the Earth, pretty much. It's huge. Or in the ocean, you can see indirectly that there's a material vortex capturing a chlorophyll spot and carrying it over large distances. Without the chlorophyll, you wouldn't see it. So the idea is, how could we visualize it without putting chlorophyll in, just from the properties of the velocity field? This is a nice elliptic tube that was pictured. Again, the references, picture credits are in my annual reviews. I don't know if you would guess what this is. This is actually a volcano puffing a torus out, and this is basically a toroidal vortex ring, again, elliptic structure. So these are not characterized by stretching or folding or attraction or lack of shear. They are characterized by the curious fact that against all odds, they don't do any of this. They somehow preserve their integrity minus modulo small changes, right? Somehow they're islands in turbulence, or the islands in chaos that don't give in to stretching, folding, and all that, right? So how could we go after these? And this PRA is a diagnostic designed for that. This is another way of getting information out of the deformation gradient. The deformation gradient also has another decomposition, as again, any square matrix would have, is that you can decompose it. So we already talked about the singular value decomposition, but there's the polar decomposition, which was invented for the purposes of mechanics, which is there's a rotation and there's a stretch component here. So the rotation is a rotation tensor, again, Lagrangian between T naught and T. And the continuum mechanics call this the right stretch tensor, which is symmetric and it's positive definite. And once you have these formulas, you can actually get to this tensor very quickly. Once you have the Cauchy-Green strain tensor, you just have to take its square root. It's positive definite, therefore you can take its square root. Once you have the square root of the Cauchy-Green, the rotation tensor, the polar rotation tensor, is just the deformation gradient times the inverse of that stretch tensor, just from this formula. Just imagine that you already have U, okay? Once you have U, then you can get to R just by using U inverse multiplying it by the grad F, just straight from this formula, okay? And here comes the observation. This is an old result from continuum mechanics. But here's the observation in the work with Mohammed, is that any 3D rotation can be represented by an angle around a designated axis of rotation, okay? And one can calculate any 3D rotation can be thought of instantaneously, not just instantaneously, it's a finite rotation, as you picking a distinguished axis and simply rotating around that axis, right? Because generally speaking, a 3D rotation we think of it as something very general, right? But the point is that when you look at just where you started from and where you ended, you can pick an axis and you can think of the outcome as rotation along that axis by a given angle. And we worked hard in calculating that angle in this context, because somehow that was not, for some reason, not computed for the polar rotation tensor. And the cosine of that angle, which we call the cosine of the polar rotation angle, is a surprisingly simple formula. It's 1/2 summing all the left and right eigenvalues of the eigenvectors of the Cauchy-Green strain tensor. You take the linear product and you subtract 1 in the end. And in 3 dimensions. In 2 dimensions, if the flow is incompressible, then the intermediate eigenvalue, if you still think in terms of 3 dimensions, even when you analyze 2 dimensions, the intermediate eigenvalue is 1. Lambda 2 is always 1. And then this formula simplifies that it's either the product of the first left and right eigenvectors of the Cauchy-Green strain tensor or the second one, either way. So again, it pays off here if you did SVD to get the FTLE, because from the same computation that gave you FTLE, for which you only use the eigenvalues of the Cauchy-Green strain tensor, you can also get the PRE and the PRA. And that there's a story behind this, that constant level surfaces of the PRA give you then elliptic structures. That we describe the reason for that, why you would expect that. So how does that work out? So elliptic LCS is in 2D, defining the polar rotation angle. These will be closed level curves of the polar rotation angle. And the outermost in a family, you could use to define a vortex, a material vortex boundary, which is objective, it turns out. The level curves of the PRA are objective in 2D. Unfortunately, in 3D, that's not true. The level surfaces of the PRA are not objective in 3D. So the PRA is a good diagnostic tool in 2D, objective in that sense. And by my own principle, I have to discount it in 3D. There's alternatives in 3D, but in 3D, I don't promote the PRA for that reason. Okay, but in 2D, I do. So how do you compute it? Same thing. It's just once you have the Cauchy-Green strain tensor, just do, or once you have the deformation gradient, just do an SVD, singular value decomposition, and a byproduct of that will be the left and right singular vectors. And there you go. You have the PRA immediately, and then just plot it. And when you do that, this is what Mohammed did. This is what you get from vorticity in a two-dimensional turbulence simulation. But vorticity is just an instantaneous scalar distribution. It doesn't quite tell you which one of these regions really captures material and carries it without breaking it up, because that's the question. And when you run the PRA, this is what you get. Very clearly delineated concentric closed curves. And the outermost you can use to define the boundary of a material vortex. Okay. And it turns out that some of the indications by vorticity, oh, is this really a vortex? The PRA answers that. No, it's not a vortex. There are no concentric packages of material that are being carried without substantial deformation. These get stretched out. So whenever you have regions like this, they really stick out. And let me give you a close-up of that. This is what you get, very well-defined PRA level curves. This is the outermost one, so that would be a material vortex boundary. And beyond that, things are just breaking up. So when you advect the red curve after 50 time units, which is long in this turbulent flow, it will get, rotated, it will get shifted, there will be little deformations on it, but fundamentally, it's not breaking up. It preserves its rotational coherence, and so does anything inside when you pick it along these curves. So this is what we call rotational coherence. But if you were just to draw a closed material curve anywhere in turbulence, and you were to advect it, you would just see it stretch and fold over the place, right? All over the place, especially in this region. So these are the ones that kind of the islands in the middle of chaos or in the middle of turbulence. If you know a little bit, maybe classical mechanics or dynamical systems and classical mechanics, these are the analogs of Kolmogorov-Arnold-Moser or KM tori that we understand very well in near integrable mechanics. No time dependence there, and near integrable. These are the generalizations of those to unsteady fluid mechanics or even turbulence. So these are islands of regular behavior. Again, you would not get them just from streamlines, but these techniques gives you those objectively. Not in 3D, and yet these examples are only 3D. So it turns out very quickly, and I'm not going to give you maybe the explanation because I know I'm using up a lot of time, but there is a relative rotation tensor that you can extract from the polar rotation tensor that tells you how you rotate relative to the mean rotation of the flow, represented by the mean vorticity. And if you then identify that tensor, which is just a factor within the polar rotation tensor, and you identify its axis of rotation, that turns out to be nothing else but the deviation of the vorticity from the spatially averaged vorticity, here normalized, so this vector. And if you just measure the rotation along that as you travel along a trajectory, that angle turns out to be, we call it the dynamic rotation angle, that turns out to be objective, and it's computable. So in the end, that material rotation angle, which is objective, is what we call the Lagrangian averaged vorticity deviation, or LAVD. And that's simply a time integral along you take the vorticity along a trajectory, you subtract the mean vorticity in the whole domain of interest, say your computational domain, you take the modulus of the two, we call that vorticity deviation from the mean, and integrate it. And this will play the same role as PRA. You can look for level curves and level surfaces, except that LAVD is also objective in 3D, not just in 2D. That's the big advantage. That's why we did it. So it's objective. And if you then, it has an added advantage. You can prove using LAVD, and this has a mathematical proof that I'm not going into, but it's in this paper, that if you then put inertial finite-sized particles in a flow, then not only does LAVD contours give you material vortex boundaries, but LAVD maxima are the vortex cores to which your inertial particles will be attracted. Sometimes they get attracted, sometimes they get repelled, depending on the orientation of the eddy, say in the data set, or the vortex, and depending on whether you have bubbles, which are light, or you have heavy particles. There's a combination of these. But whenever you have a combination that there's a well-defined core in your experimental observations, the theorem tells you that the inertial particles have to be attracted to that LAVD minimum. So that then gives you a well-defined vortex core for which we never had a definition before, but in a material sense. And this is an actual simulation which was really preceded by the theorem. And we really wanted to see whether this is true. So these are simulated debris, and these are vortices, LAVD contours calculated from the Aviso altimetry data set. So this is a satellite-based data set that we describe in these and many other papers, okay? So when you run that simulation, look what happens. The debris is the green one, and it really nicely in each and every case converges to that black dot. The black dot is just the LAVD maximum, right? So that was stunning to see, because this was really an example in which there was a mathematical prediction for something we had never nailed before. We thought it was maybe the minimum of the FTLE, that would be the vortex core. No, never worked out. But this one, LAVD minima are the ones that you would actually observe in a flow visualization experiment, as this simulation shows. I think there's one more question that, again, unfortunately, I can't read it, but if somebody could read it for me.
Yes, I will read it for you. I just waited. The question is it possible to find the thickness of attracting structures using LCS? The boundaries are usually seen in experiments using dye visualization, thermal pumps, for example.
Right. That's an excellent question. I was sort of alluding to this before. This whole theory looks for a theoretical centerpiece, which is just a single curve or a single surface that doesn't have a thickness. When you release dye, then you have a patch initially, and all those particles will be on their way, right, towards that single thin structure. When you take a finite time snapshot, a finite time open set cannot ever collapse down to a single line, okay? So you will always perceive a finite thickness for any observed pattern, but the thickness of the pattern is not to be mixed up with the thickness of the LCS. The LCS is infinitely thin, okay? It exists as a most repelling material line, most attracting material, and so on, which is perfectly well-defined theoretically. But the tracers that you use to highlight it are on their way to it or being, pushed away. So that's why you see a finite thickness. And that's quite honestly one of the reasons why we need the LCS theory. Because when you see a finitely thick slab, who's to say where exactly the centerpiece of that behavior is? And that's what the theory tells you. The experiments can confirm it to the extent that, okay, here's my prediction. And then this, cloud of tracers is kind of shrinking onto it, right? But it will always have a finite thickness, and that we cannot predict from this theory, because that's a function of many things: how you initialized the tracers, how long you waited, how long has the LCS been living, because it may be losing their stability, and then all of a sudden or attraction, and all of a sudden that slab will no longer be thinner and thinner, but it's going on to do other things. It gets attracted to other things, right? One more question I see there, please.
Yes, just a question that just appeared. Can LAVD extremum coincide with track the ocean surface drifters?
Right. So there will be two cases again, depending on whether it's what's the orientation of the eddy, clockwise or anti-clockwise. You're on the northern hemisphere, on the southern, there will be different combinations of these. That's in the paper. The theorem accounts for all those combinations. But whenever you will have a converging drifter, excuse me, rather than a repelling, rather than one that spirals out, whenever you have a converging one, and whenever that drifter, to a very good approximation, obeys the Maxi-Riley equations, then it has to go to the LAVD maximum. That's luckily a theorem. If there are other effects, right, whatever, there's very strong windage that blows it away or other things, then that can be a perturbation to this. But for all we know and for all we have seen, they have to converge in those cases. Or if they get repelled, then the theoretical centerpiece of repulsion will be that point, the LAVD maximum. I think we're okay now, right? There's no more questions?
Yes,
or
no more question.
Yeah, okay, thank you. Very quickly, so this is a 3D calculation from LAVD. That's the Southern Ocean State Estimate, which is a data simulating 3D ocean model. And this was work by Alireza Haji Gassem. He did great work. What you see here, these really messy surfaces are the level sets of the LAVD outside the elliptic region. So this is how bad it gets, right? There's no rotational coherence there. But right in the middle of it prevails this beautiful, three-dimensional eddy, and you can also identify the core of that, which is basically a ridge of the LAVD field, the maximum ridge, and Alireza identified that. And if you then want to see whether this is how this moves, and this is another snapshot of this, is what he identified in the data set. And the test of the pudding, which unfortunately a lot of people don't do, you can make any claim that you want that this is a material vortex or coherent vortex and put it in a beautiful picture in a paper or on a slide. But then you have to show that if you then indeed advect that, if you take the flow map, if you calculate trajectories from those points, then it doesn't lose its coherence. And that's a very tough test because it's a 3D turbulent flow. So it has this set of trajectories has every incentive to get mixed up and stretch and fold. It's a big deal then to find something. It's not a big deal to label something as an eddy. It's a big deal to label it in a way that a material eddy, so that it really behaves coherently when you run those trajectories running from this point. So after this long introduction, that's exactly what Alireza did. And look what happens. It can wobble, it can develop a little bit of little riblets here, but fundamentally it stays coherent because it's being constructed based on a coherence principle. It's not falling apart. We have also papers in which we show you just slightly off, you shift this complete mess, okay? Gets completely mixed up. This is what I very quickly want to get to. Instantaneous limits of LCSs. Why would we care? Well, there are lots of phenomena in fluid mechanics in which actually we don't have an a priori associated time scale with it. And all these Lagrangian diagnostic tools require an integration time. The Cauchy-Green strain tensor is calculated over a given integration time or something like that, right? So we would need to know that. But very often the transients are important and we don't want to average them out. And also mergers and breakups, this is very important, cannot be handled by Lagrangian analysis because pure Lagrangian analysis, consistent one, because two material points will never become one if you have a decent smooth velocity field, or a material point cannot split into two. Two material structures cannot ever collide and merge. They can get very close to each other. And that's what you see. This is a vortex merger simulation. And you see these two different, by Monet and others, very nice pictures. These two different dye spots in the Lagrangian frame, they get very close to each other. They start dancing. And unless diffusion kicks in down the line at some point, these streaks preserve their initial identity. So if I was surrounded by green guys, then I will keep being surrounded by green guys forever. We get, it's gonna be a bit tight in there, but we never lose that kind of integrity. And the same can be said about the red. Ultimately, if you have diffusive dye, then diffusion will even things out, but they remain separated from each other forever, right? And that's not the case in the Eulerian frame. And very often in the Eulerian frame, it's helpful to think about, just kind of forget about those details and consider these two vortices to be merged for practical purposes, okay? And that's what Lagrangian techniques cannot do. So the resolution of this, and again, the Eulerian techniques, at least the lambda to delta Q, they in principle can do that. They have no problem with that, okay, when you evaluate them instantaneously, except that none of them are objective. So if you want to maintain your expectation for physical observability, consistency across observers, and so on, then passing to these is not the solution. What is then the solution? The idea would be, let's take the short-term, infinitesimally short-term limit of LCSs. Thereby, you keep all the advantageous properties of LCSs, okay? And they're going to be objective. But since you only calculate them over infinitesimally short time intervals, they will no longer be actually material, okay? Because it's always just relative to this point. So an instantaneous LCS computed at this point in time and that computed in time, they don't have to evolve materially into each other. And for that reason, the upside of that, you can get mergers, you can get breakups, whatever you want, right? But the good properties are still preserved. So what are the instantaneous? So the instantaneous limit of the Cauchy-Green strain tensor, when you start from T and go to T plus tau, you can do a very easy expansion of that. It's basically the identity plus 2 times the time that tiny time tau times the rate of strain tensor, which I've already mentioned, which is objective. That's good, right? So the idea is deal with this, the leading order one, and take the limit of tau equals 0 whenever and whichever way it's convenient. If I just blindly take tau equals 0, I'm not getting much, I'm getting identity. But if I then take appropriate quantities that do bring out this term as well, or I'm interested in the time derivative of those quantities, then I will get to the next term in the development of the Cauchy-Green strain tensor. It's over here and it's objective. So when you do that, the instantaneous limit of the FTLE is just the largest eigenvalue of the rate of strain tensor. So whatever you use FTLE for, you can use the largest eigenvalue of the rate of strain tensor, but that's the Eulerian, proper Eulerian objective limit of it. Instantaneous PRA, that's unfortunately a bummer. Whichever way you work it out, it just limits on 0. So that's not something that's giving you anything in the instantaneous limit, but LAVD does. So the instantaneous limit of LAVD is IVD, which is simply instantaneous vorticity deviation, the difference of the vorticity from its spatial mean. You can plot that and it's objective. Vorticity is not objective, but if you subtract its spatial mean, that becomes objective. And again, you can use that to define instantaneous vortices, no longer material, but objective. And they are limits of LCSs. And I forgot if I had pictures for this. Yeah, I just wanted to give you quickly how this improves your instantaneous, because instantaneous is also varied for short times, okay? So it's not just for that, because of this expansion. If I identify this part of the expansion, I'm still okay for small times because the correction is small, right? So that still gives me a short-term prediction horizon. If you simply calculate streamlines in a flow, then we used to think that the stagnation points are the main players, the saddle points. So these are instantaneous saddle type stagnation points, okay? If you put material around them and you simulate this is what happens. Yeah, some of them stretch indeed. This one, not so much. It's not clear why. But also we would think, okay, there's nothing else stretching in this flow, nothing else interesting. Unfortunately, this is a very frame-dependent way of assessing stretching because it's based on instantaneous stagnation points. Those are they're not even Galilean invariant. So if you start then looking for the maximum of the local strain and the corresponding eigenvectors of the strain, you actually get an objective notion of an instantaneous saddle point as well as the unstable direction associated with that. So those will be the green objects here. Look how many we have. And some of those are in fact happen to be close to the stagnation points. That's why these two stagnation points got lucky, because there were objective counterparts nearby. But according to this picture, there are many other opportunities for material stretching in the flow. And also we now understand why this guy didn't stretch a whole lot, because there wasn't anybody nearby. So if you run this now, sorry, how do I run this? It doesn't want to run. Okay, see what happens? That all those objective saddle points were really saddle points, and we were completely missing them based on the streamline picture. Look at how much they were stretching. And this guy was not stretching because there was no objective one nearby. And these others, we just simply got lucky because in that frame, they were marking objective ones, but they are, if you hop on an airplane, which goes fast enough, you will, in that frame of the airplane, you will see no stagnation points in this flow. So not that we would have missed even those two. You know what, I'll stop here now because I had maybe a couple more slides, but I guess I can just go to those tomorrow because I don't want to, I'm probably already exceeding my time allocation. My apologies about that, and thanks a lot for your attention.
Thanks a lot. Thanks for this very, very interesting lecture. We have a few minutes for some questions. You were perfectly on time.
Thank you.
So if there is some question, you could write it on the chat or unmute and ask your question.
Why people are thinking about that, maybe that I showed them my last two slides. These concepts have been used, in fact, in C experiments. When we were, this was a project that was run out of MIT. The head PI on that was Tom Peacock, who's also relevant in the sense that it was Mani Mathur's main advisor. I was at MIT. I was his co-advisor. And this is a large project that also involved the US Coast Guard. Art Allen was the chief rescue mission designer. I think he retired by now. And several people from Woods Hole. Matthias Serra, who's a student of mine, he's now a professor at UCSD. But we were basically asking, can we ask this concept, objective Eulerian coherent structures in search and rescue operations, which are characteristically short timescale problems. Unfortunately, if you don't find a person in 6 hours in the ocean, then the search is reclassified as recovery, because the chances of them being alive are very small. Okay, so you really have to find people very quickly. And our idea was that maybe there are these objective saddle points in the flow, and their unstable manifolds are attracting people. Okay, and we want to find them in an objective sense because this is a high stakes problem. We don't just want to make an error based on false positives or negatives. So we would locate these points from available velocity data, typically models that the Coast Guard runs, very quickly assess where they are, and the search mission would be then informed by those, the locations of the strongest, what we call traps. These are transient attracting profiles. But what you see here is the maximal rate of strain point, and this direction would be the maximal eigenvalue of the rate of strain that we would get. And Mattia actually did this real time. He was in one of those ships. There were no helicopters nearby, but he was advising the crew on these ships where to deploy buoy, and to see whether they really go to these points. And not only did they also deploy drifters and mannequins. This is an actual picture of that. And this was, Mattia would make his predictions, and these were the deployment sites of mannequins and drifters. The drifters are white circles, the mannequins are triangles. Why did we do both? Because we wanted to see whether there is a dependence on the attractiveness being attracted to the trap on the shape of the object, or so the buoy are clearly different from the mannequins, and mannequins are closer to humans, right? And these were Mattia's predictions as of 10:15 on that day, 2018. And these were the release sites. The ships were releasing objects, modeling people as if they were falling in water, right? And Mattia's prediction was that these are the main traps, the strongest attracting transient attraction profiles, and we have their strength of attraction because we can calculate the eigenvalues of the rate of strain. And lo and behold, this is what happened after just 1 hour. They're approaching them, both the mannequins and the drifters, and in 2 hours, they're really aligning with them. And this was just remarkable. And that's where really Art got sold on the idea, because before that, he was just very skeptical because they had all these algorithms that they would run, usually lots of stochastic models and average and this and that. And this was just based on one velocity field and prediction. And this is what I've been telling you, that yes, formally it's an instantaneous assessment, but it's also the leading order expansion on a time series. So when you're interested in short-term predictions, then the OECS, the objective Eulerian coherent structures, are very valuable. And this was really in an ocean setting. And as we understood later on, the Coast Guard was following up, and they started implementing this in their toolkit. Sorry, there was an excuse to take more time, but I see that at least inspired one question.
This is very interesting. There's a question. Can you expand on the relation between the lapse time of the CG tensor and the flows with multiple time scales? For example, bulk versus boundary layer stratified convection.
That's a good point. I mean, the Cauchy-Green strain tensor, you can compute over different time scales. You will get different answers. Reason is that unsteady fluid flows are not like steady fluid flows. If you ask what the Lagrangian behavior is over this time interval, who's the most influential material surface over this time interval, and then you ask who's the most important material surface over this time interval, the answer is not the same because structures are coming and going. So you will only, you gotta have a time scale in mind over which you're interested in the behavior. If you don't have one, you can do one or two things. Implement different timescales or go to OECS, objective Eulerian coherent structures, because those have no timescales associated with them. They're just basically always instantaneous short-term predictions. And then if there's something really sticking by and there for a long time, then you will keep recovering that from these instantaneous calculations. But by doing instantaneous as opposed to a fixed time scale, you also are giving a chance for the flow to change and create new structures and destroy ones. So I would say if in a flow, if you're in a situation where you have a favorite time scale that you need to explore or several, then explore those and use them in the Cauchy-Green strain tensor. If not, you might actually, what we do in a data set with Lagrangian, we do Lagrangian analysis, we just simply run it over the whole data set to begin with, okay? But that will pick you only things that have existed all the way. If you then want to say, I want to allow for changes and transients and everything, I would take the other limit, which is the OECS, the instantaneous one.
Okay, I will read a last question and then we will have a short break before the next lecture. So the question is, so one of the things people use to justify studying eddy tracking and so forth in the ocean is that the eddies identified, for example, by the SSH-based measures, do a lot of tracer transport and contribute significantly to the circulation, which could be slightly dubious given the lack of objectivity. Was wondering if you have any comments on this. I know you have a paper with Ryan Abernathy on this.
Correct. We have several papers in. We went after this claim. And pun intended, we believe that this claim doesn't hold water, with pun intended, because we actually took SSH contours. And instead of giving arguments why it should be carrying traces, we actually released trajectories from them. And you can find it we have a JPO paper on this, several papers. You can go to my webpage, but also in my annual reviews. Unfortunately, they do collapse very quickly. They disintegrate. I don't hold it against them because though SSH contours are instantaneous predictions, they don't contain information about the past and the future. It would be very surprising if from that one instantaneous measurement, you could predict the long-term behavior of traces in there, right? What we do with LCS uses a whole lot more information because we're integrating trajectories on that. So in many ways, it's almost an unfair comparison because we're using lots of data rather than just one snapshot, okay? But I can confirm definitely that in my experience, the SSH contours, and you can look at our papers, we did this in several ones, they're very insightful constructs, but they do not preserve their coherence. These ones and they are not objective, as you also pointed out, and you could, in fact, by my logic, you could, for material mixing, you could discount them as those not meeting the litmus test, okay? I have to pass on an anecdotal assessment of those that I don't want to name anybody nor can I, but I heard it from a colleague in oceanography who said that he was talking to a marine biologist group who went out and wrote a proposal and the proposal got funded. They got ship time. It's not cheap to pay for the ship, and they wanted to study marine ecosystems and how they, predators, preys, and whatnot, they interact with each other. The best place to study these is large oceanic mesoskeletes, because then these algae are carried, and then you get the fish who are chasing the algae, and then you have the predators, and you have the birds. These are little ecosystems. Now you have the ship. Now you have the ship time. Now you're ready to go out. What do? You have to know where these are, right? So what then the people did there, they went for the updated SSH picture, which are incredibly useful, by the way. Don't get me wrong. This is a fantastic tool. It's available. The only question is whether you can really use it for material transport. That's the only question. It's a tremendous service to the community, and I applaud. There's very distinguished people involved in that. I'm not criticizing that. I'm just saying that if you want to use that for material transport, are they reliable? So again, they downloaded the latest SSH pictures. There you go, huge eddy there. We should be going there. They went with the ship there. They didn't find anything. So that had very real financial consequences in that case, because they were simply not finding the kind of materially coherent transported ecosystem that they thought would be finding there. Okay, so that would just sort of be anecdotal evidence to my statement that in reality, these are much the same way as we have found in simulations. The water masses surrounded by SSH contours do not keep their coherence over time.
Thanks a lot again for this nice lecture. If someone has another question, maybe you can send us the question by email, or we will send the question to George before tomorrow, so that
absolutely,
we have an answer for the lecture tomorrow. Thanks again for this nice
Thank you again, and see you tomorrow. Thanks again for the opportunity. Really enjoyed the questions. Thanks to everybody for listening and for the questions. Take care.